Welcome back, students, in a series of videos done on capacitors. Today we are going to talk about capacitor and its type. Okay, now in the previous videos we have said that these capacitors, they are made up from the conductors, right? They are made up from where? From the conductors, and bigger the conductor, bigger will be its capacitance. We had seen that from the expression that if the radius is bigger, then the capacitance is bigger, right? That means what? If we have a big conductor, then its capacitance will be large, right? But normally, in a machine where the capacitors are used, we have seen that the capacitors are very small in size. Okay, somehow of the size of a small ones, cylinder type. You may have seen that they looks like a cylinder types, and there are the two terminals. Okay, so some farad unit will be given depending upon the capacitance. So how its capacitance is made big, right? And how come its capacitance turned bigger? All right, then basically in your syllabus we will see there are, basically in your book there are three types of capacitors which is discussed. Okay, one is parallel capacitor. Okay, parallel capacitor. My handwriting is not coming good. Parallel capacitor. Then even spherical capacitor. Then another is cylindrical capacitor. Okay, cylindrical capacitor. Okay, cylindrical capacitor. The most common capacitor. Okay, the most common of them, parallel capacitor, spherical capacitor, cylindrical capacitor, the most common one is parallel capacitor. Like I have made the previously that it looks like a cylinder, right? But these are parallel capacitors. Okay, so how it is made, let's discuss it. Okay, let us discuss it. In a parallel capacitor, basically it comprises of two plates. Okay, I'm talking exclusively about the parallel capacitor because this is important for your study and for your exam also. Parallel capacitor, what it is, it looks like a two plates. Okay, there will be two plates, and the two plates will have small separation in between. All right, the areas of the plates will be the same. Okay, the area of the plate will be the same, and the charge on both the plates will be the same but opposite in direction. Like suppose this is positively charged, okay, then this will be negatively charged. Okay, it's equal. If this positive plate has a charge density of sigma because it's surface, right, then it should have what? Minus sigma. One more thing, again I'm saying, the charges on the capacitors is the inside of the plate. All right, the charge will not be outside. Okay, so there are two plates, positive and negative, equal, okay, having the same area, and this is the parallel plate capacitor. Then one more thing. Now what is the total charge? The total charge in capacitor, the total charge, you may call that sigma and minus sigma 0, but we don't call that. We will only consider this one only. All right, so the total charge in this case we called it sigma, not sigma minus sigma equal to 0. We will only take the positive plate in order to compute its charge. Okay, actually then this negative is formed by means of induction. Okay, so we are not going to consider this one when we are talking about the charge. The total charge of a capacitor is sigma. All right, this is the main plate, and near this plate there is another plate having the equal charge, and the total charge of the capacitor is sigma. I'm repeating it again. Okay, it is purely because of the induction. Okay, how exactly? Actually, suppose here is a positive plate. Okay, let's say inside only, let's say there is positive charge. Okay, now near to it, okay, near to it, let's say I have brought another plate. Let's say I have brought another plate near to it. Then what will happen? Because of the induction, the inside of the plate will be what? Will turn negative, right? Equally. And the outside of the plate will turn what? Positive, right? This is because of the induction. Now this side, the outside facing plate, will be always connected to the earth. Okay, it is always grounded. All right, fine. Now, as earth is a very good conductor, what will happen? All the positive charge of it will flow back to the earth. Okay, so and this negative charge, now you may say that this negative charge also should flow. It will not going to flow. The reason is because the positive will attract it and it will not allow the charge to flow to the ground. Another thing, as the negative facing plates are inward, so it will stick. Okay, it will stick here while all those positive will go. So whenever we talk of a capacitor, we will represent it by this way, but we will call the total charge is sigma. Okay, because minus sigma is because of the effect of the sigma. Understood? All right, so this type of configuration where the two plates are kept parallel plates, kept parallel to each other, separated by a very small distance, this is known as a parallel plate capacitor, and the total charge is sigma. Remember it. Okay, now what happens? How the capacitance will get increased when we do this thing. All right, we will learn about that. Okay, in the beginning, let me just make it. All right, now we had seen, suppose here is only single plate. Okay, then if there is a single plate only, then depending upon the size, now in this case the area is the size. Okay, depending upon its size, what it will have some capacitance, right? But if I keep another plate very near to it, let's say the distance between the plate is d. Okay, then right, okay, then we had done in Gauss law, Gauss theorem, then we had learned that outside the plate electric field is what? Zero, right? Outside the plates electric field is zero, while in between the plate electric field is sigma by epsilon naught. This I had done in a derivation in Gauss law, but later on this portion of it was omitted. Okay, that's why you need to keep in your mind, if this type of configuration is there, then just outside the plates electric field is zero, while the electric field is purely in between, and that electric field is, the magnitude of that electric field is charge on either plate divided by epsilon naught. Okay, so this electric field in between is a uniform field. All right, okay, now what about the capacitance? Okay, see, what happened is that when we talk about in theoretical, the presence of negative, okay, the presence of negative will reduce the potential. Like suppose when there is a conductor, single plate only, all right, when there is single plate only, when you are putting the charges, all right, one charge you put, another charge you put, what, another charge have to face the repulsion due to the first one, right? So it will be harder to put this plus here. If you put further, the stronger the repulsion will be. If you put further, stronger the repulsion will be. So what? The potential of it will keep on increasing, right? So there comes a stage where it will not able to bear any further charge. Yes or no? Means what? Its potential get maximum, and as its potential get maximum, it cannot bear further charge, right? So, but because potential is the work done in bringing the charge, right? But if you are keeping negative near to it, all right, if you are keeping negative near to it, then the overall charge of the system will get somehow reduced, isn't it? If the overall charge of the system get reduced, then what will happen? The potential of it will reduce, right? And capacitance is what? Charge per unit potential, right? When the potential is reduced, what will happen? The capacitance will increase. Okay, see, positive and presence of positive and positive and positive and positive, what will happen? Bringing the charge, it gets difficult. It gets difficult, right? More repulsion means what? The potential of it will get increased, right? But in their system, if there is negative, then the overall charge of it will reduce, right? Then what? It will become much easier. Then means what? The potential will reduce. When the potential is reduced, the capacitance will increase. Okay, this is the basic theory about it. All right, now coming about the parallel plate capacitor. Okay, outside is zero electric field, but in between the electric field is there, which is uniform. Sigma by epsilon naught. You need to remember it. All right, now capacitance is equal to, right? Fine or not? Okay, now charge Q is what? Charge on either plate. Let's say sigma, let's say minus sigma, let's say A, let's say A, same area, right or not? Okay, then charge, all right, charge density is what? Charge density is charge contained in unit area, right? Charge contained in unit area. In the unit area, how much the charge it contained, that is charge density. In A area, how much the charge it contained? Sigma into A, right or not? Right? So, for area A, the charge contained is sigma into A. I hope you will understand it. Then this Q will be what, student? Q will be what? Q will be sigma A by V. This derivation is important, I'm telling you again. All right. Now, is there is any relationship between potential and electric field? Because in between the electric field we need, right? Then we know we have the relation between potential and electric field. That is what? Electric field is equal to the change of the potential with the distance, right? Right? Okay. Electric field is equal to the change of the potential with the distance, right? The presence of electric field confirms that the potential will change with the distance. Now in this bit, in this region, there is electric field. That means what? That means what? The potential will change as we are going from the plate 1 to plate 2, right? And what is the direction of the electric field? This is the direction of electric field. Means what? In what direction the potential is reducing from the first plate to the another, right? Fine. So the potential, in this case, let's call the potential as V. Okay, let's say V is the potential between the two plates. Okay, so can I, and what is the distance? The distance is D. Minus says what? That potential is decreasing. So what? I can, minus only tells the direction, right? Negative says the direction. Says the direction. So ignore it. All right. We already know the direction. Ignore it. All right. V is what? The difference. V is the difference of potential between the two plates. Okay. So this formula will become V and D, right? Then what is V? V is equal to E into D. And what is E? E is sigma by epsilon into D. All right, call this one equation number 2. All right. Now what we need to? We need to get the expression of C, right? Now substitute it. Okay. So C will be equal to what? Sigma A, in place of V, what I can write? Sigma epsilon naught D. Cancel out. Then what will happen? Epsilon A by D. So the capacitance of the parallel plate capacitor depends upon the area, depends upon the separation between the plates. Bigger the area, higher the capacitance. Smaller the distance, higher the capacitance. So normally what we do is we keep the separation between the two plates so less in order to have large capacitance, because we can't afford to make big area. All right. Okay. So this is the information we get in parallel plate capacitor. The capacitance depends upon the area and depends upon the distance. Okay, so the dimension of the plate and how they are kept is very important in order to determine its capacitance. Thank you.